Hello students, welcome back. We have one more section to go, and that's section 5, constant coefficient linear systems. For now, I'm going to cover it as a part of lesson 14 as planned, but after all is said and done, it may end up moving to lesson 15. If it happens, so be it. In any case, for now, let's focus upon this system. A first-order, non-homogeneous system of linear ordinary differential equations with constant coefficient matrix. Again, A is a constant coefficient matrix. If you have A of t, things are far more difficult. Now, previously, we didn't have this part because we had been dealing with only homogeneous systems. Now we have to consider the non-homogeneous part. In the end, what do we expect? This is what we expect. Solution of the homogeneous equation plus a particular solution. This one, the solution of the homogeneous equation, which I'm highlighting in blue, is something we had been dealing with. And this one, this is new. In the end, we have to add them up. Now, how are we going to set up this? We're going to employ the same method that we used way back in week 2 when we were studying the first-order linear equation. We're going to use the method of integrating factor. Flip this one to the other side, to the left-hand side like this, and then take the coefficient part here and take the exponential of the antiderivative of the coefficient function. In this particular case, the coefficient function is just a constant function, negative a, where a is a matrix, a square matrix. So the antiderivative is negative at, and the exponential is the matrix exponential e to the negative at. So that's the integrating factor. I just highlighted it in green. What we are going to do now is to multiply this integrating factor to both sides of the equation here, to the left and also to the right. Here we go. I just multiply this matrix exponential here and here and also here. Make sense? Multiply by the same thing to both sides of the equation so everything is okay. And also, this is an invertible matrix. Remember that. Exponential is always invertible. Matrix A may or may not be invertible, but exponential is always invertible. The inverse of e to the negative at is e to the positive at. Another thing that you have to remember, the exponential here, e to the negative at, and a commute. They're commutative. This is what I'm talking about. E to the negative at times a is equal to a times e to the negative at. Why? I'm going to leave it as an exercise for you. If you put this one into the Taylor-Maclaurin series expansion and this too, and then multiply a from the left-hand side and right-hand side to each individual term, you'll see. Detail is left to the students. All right. From here, by multiplying the integrating factor, we got that. So everybody got it, right? Okay, I don't need this separate color anymore. So let's come back to black. Now, left-hand side can be written as a single derivative by product rule. The red part, if you take the derivative of this red, this is what we get, including the sign. Oops. This should be red. And then the derivative of this blue part, y, is this one. So this one is a product rule structure. And indeed, you can combine those into a single derivative using the product rule. No problem there. And then in the right-hand side, well, same as before. Okay, we have only one derivative here and one expression there. We can integrate both sides. But then again, we always use the definite integral here, because in chapter 9, if you use indefinite integral, then sometimes, as a matter of fact, very often it becomes a problem. And how do you deal with this? Plus c is often a problem. So always we use the definite integral and take the definite integral from t0 to t, where t0 is the initial condition. Now we have the definite integral and the derivative. So by the fundamental theorem of calculus, they cancel each other out, and basically we just plug in the top and plug in the bottom and subtract. So plug in the top, u equals to t, and plug in the bottom, u equals to t0. As a matter of fact, this should have been t0 because u is t0 for the second part, u is t for that one, the top and bottom of this integral. But then again, what is y of t0? It's y star. Because of the IC, it can be reduced as y star. And there you go. Okay, so far so good. Now from here, let's solve for y. Flip this one to the other side, and this is what you get. All right, and then divide out by this exponential. And can we do it? The answer is yes, of course, because this is always invertible. Remember, I reminded you just now, a may or may not be invertible, but exponential is always invertible. The inverse is exponential of positive at, and multiply that to both of these. And then simplify these to exponential, and we have this expression, also that expression, and here we go. And the blue part is the solution of the homogeneous equation. And the red part here is a particular solution. Okay, that settles it. Now, we got up to here, so I'm not going to go back and redo all those derivations. From this point on, I'm going to focus upon how to use it. Okay, this is something we are going to focus upon. Keep it somewhere. And let's do an example problem. Ready? Okay, we have a system, a non-homogeneous system, as you can see here and there, and then we have an initial condition here. All right, how do we handle that? Well, look at this solution here. Solution formula requires matrix expression. So it looks like we'll have to bring it down to matrix expression. So y1 prime, y2 prime is equal to, let's look at this part, minus 1, 2, minus 3, 4 times y1, y2 plus the non-homogeneous part, exponential of t, and then minus 2 exponential of t. So that takes care of this part. And then the initial condition. That's equal to y star, which is 1, 1 in this particular case. So we have the matrix expression of the system. Was it easy? It should have been. Well, here's a solution here, matrix expression. And then if you name those accordingly, then you're going to get much simpler expression. And based upon this, you're going to get this solution. Okay, all right. First preparation is done. Now let's look at the blue solution. That is the solution of the homogeneous equation. How do you do that? Well, this is exponential, the matrix exponential times y star, and y star is right here. Multiplying by this 1 is not going to be too much of a problem. Finding out this matrix exponential is going to be a big deal. So basically this is what we want. A t. By the way, t0 is 0, so I don't have to worry about subtracting by 0. So this is what we want. And do you recall how to find this? Laplace inversion of what? Si minus a. Remember? Inverse. Remember this? This matrix is called the resolvent matrix. So let's find out this resolvent matrix. Si. Alright, this is my A. So basically it's this computation we are doing. We need S. Therefore, we have here we have S minus of -1. So we end up with S plus. And here 0 minus 2. Here 0 minus of -3. And here I have 0 minus S minus 4. So there goes the resolvent matrix. Oh no, not really, not resolvent matrix yet. The inverse of this is the resolvent matrix. How do you get that? By the inverse matrix formula, crisscross, AD minus BC, so 1 over S plus 1, S minus 4, AD, minus BC, -2 times 3, negative, positive, plus 6, times matrix, and then we have to switch the principal diagonal, and then take the negative of the others, and that is the resolvent matrix. Let's see, some simplification is in order. Break it up, we have s squared minus 3s plus 4 minus 4. S squared minus 3s minus 4. And then I have plus 6, so we have plus 2 in the end. And then let's see, I can simplify this thing, or I can factor this further. So this whole thing will become s minus 1, s minus 2. Okay. I'm gonna have to divide this from each term. Each entry rather. Okay, almost done. And we have to decompose this by partial fraction. And the denominator is s minus 1, s minus 2. Yeah, all those. We don't have any other fancy denominators, so looks okay to me, but still, decomposition by partial fraction is a lot of work, a lot of tedious work. So I'll cheat. I'll just use computer algebra system, a part command from Mathematica and get it done. And that's basically it. Up to here we got, and then the last expression here is coming from the computer algebra system. I just used a part command, and from that I have this resolvent matrix. And now I'm ready to apply the Laplace inversion. We have this fraction, 3 times 1 over s minus 1, so 3 times e to the t power, minus 2 times 1 over s minus 2, so 2 times e to the 2t power. And we can repeat things like this for each entry, and here we go. That's a Laplace inversion, and that is the matrix exponential e to the at. Almost there. This times y star, and you're gonna get the solution, the blue solution, the solution of the homogeneous part. What do you think? This part, just step 2, is kind of like entire problem that you saw in the previous exercise set. Matrix form, all right, and matrix exponential through the Laplace inversion method. Take it apart, decomposition by partial fraction, and then Laplace table, page 123. And then finally, exponential times y star. We get the solution of the homogeneous equation. Okay, blue part is done, and this part is done, and then we are going to add it up later. Alright, how about the red part? How do you calculate this thing? We have matrix exponential here, and do we have to go through this Laplace inversion again? No, not really. We already found e to the at, so in place of t, I'm going to replace by t minus u. You see, e to the at minus u, so instead of e to the at, previously we found out, where is it? Yeah, from here, replace t by t minus u, and that's what this is. And here I need f of u, so instead of e to the t power, e to the t power, we want e to the u power, e to the u power, like that. So this matrix exponential times f turns out to be like this, and that's the integrand. It's a heavy-duty computation, but given time you can do it. As a matter of fact, I cheated. I used Mathematica command for that. So if you do it right, you're going to get this expression. Now that we got the integrand parts done, let's take the integral from 0 to t, integrate from 0 to t, and we have this computation and that computation. Eventually, we have this solution and that solution. That gives me my particular solution, the red solution. Fundamental theorem here, basically. So red part is also done. So putting these two together, we have it here. The blue part is this, as we calculated before in step 2, and the red part is this one, as we just calculated in step 3. I think you can stop here, but if you just go ahead just one more step, and we have final solution like this. And this Mathematica computation, as a matter of fact, will verify all that. y1 is the top, y2 is bottom, y1 and y2 like this, and plug both of them into the system. It works out. Holy cow, that was a long problem. But then again, it was a complete problem. So I'm really happy. I completed at least one total complete problem. So here's a system, get the matrix expression, and then homogeneous part, the particular part, and then add them together. That's it.